Hello, welcome to another video. So in this video what we're going to do is we're going to go over examples that involve friction, okay? So everything we've done up until this point, we've kind of just been working with frictionless systems. And so we'll finally see what happens when we actually add friction, okay? So for this first example, if you remember back when we were first starting out doing force examples, we did one very similar to this, okay? Only the one thing that has changed now is we've added friction, okay? So given a coefficient of kinetic friction of 0.3, okay? And we'll see what happens when we actually do that. So very first thing we do is the same thing we do every single time. We're going to draw our free body diagrams, okay? And so for the box, there is the force of gravity, okay? There is the normal force, which points up. And then for this problem specifically, there's a force of the box being pulled to the right, okay? And this guy happens to be 40 newtons. We can add the angle if we want. So now, the one thing that's different is friction, okay? So friction will be parallel to the surface you're on and point opposite to the direction of motion, okay? So friction will point opposite to the direction of motion. If we're moving to the right, friction will point to the left, okay? Whatever the motion is between these two surfaces, it will point left, okay? So we write it like that, force of friction. We can add a K here to denote its kinetic friction because we're moving, okay? So now we do our free body diagrams, okay? So we'll just do FP cosine theta equals, or minus the force of friction, because that's now in the x, right? Here's our coordinate system. So minus the force of friction, and that equals the mass of the box times the acceleration of the box. In the y direction, we have Fn minus Fg equals 0, okay? And so now we want to know the acceleration of the system, right? And so we need to solve this guy. We need to solve x. So if I write this out, Fp cosine theta, we need to break down what the force of friction is, okay? And so the force of friction is equal to the coefficient of kinetic friction, which is a number between 0 and 1. And the closer it is to 1, the more friction there is on the surface, and the less friction, or the closer to 0 is, the less friction. And this is times the normal force. So we're going to just plop that right in. So this is going to be equal to the coefficient of kinetic friction times the normal force. And that's equal to MA, okay? So now the coefficient of kinetic friction is 0.3. But what was Fn? Well, now we have to look at the y equation, okay? So friction is determined by how much contact that object has with the ground. And so of course it's going to be a function of the normal force, which is usually a function of gravity. So if we solve this equation, we would see Fn equals Fg. So we can go ahead and plug that in there. So now our equation to solve for acceleration is this. We can go ahead and turn this into mg. And now we just need to divide and then plug in all the values. So this is going to be Fp cosine theta minus mu k mg over m. And that's going to be our acceleration. So we have 40 newtons times cosine of 30 degrees. Cosine of 30 degrees, if you remember, is root 3 over 2. Yeah, it was 30 degrees. And then we've got the coefficient of kinetic friction here, which is 0.30, times our mass, which was 10 kilograms, times gravity, which was 9.8 meters per second squared, divided by our mass, which was 10 kilograms. Okay? And so what we get when we do the math on that is we get 1.1 meters per second squared. Okay. So it works very similarly to the problems that we've already done. The only change is that we add this frictional force. Okay. And if you look back at the other example we did, you'll see it's very, very similar. Okay. And in fact, when we solved that last problem, this was what our solution was. And if it was frictionless, we would just get rid of this. Okay. So you get the same problem with that, with the force of friction, subtracting away. Okay. And so that's usually what will happen with these solutions. Okay. So that's pretty much this example. Let's go ahead and do another one. So for the next example, we're going to go ahead and revisit the Atwood's machine problem that we did before. Okay. It'll be the Atwood's table. So 2 boxes are in a system as shown below, and we want to know the acceleration of the system. Okay. So we have mass A. Hanging over is mass B. Okay. We have given a coefficient of kinetic friction between MA and the table. Okay. What is the acceleration of the system? And so what we'll see is we have plus x pointing that way and plus y pointing down. I want to choose the direction of acceleration as positive, so that's why I made down positive. And so now we're going to do our x and y equations. And as you'll see, these will be the exact same as the previous time we did this, only now we've added friction on top. The one last thing I forgot to mention is that MA is going to be 5 kilograms and MB will be 10 kilograms, just like before. Okay? So, let's go ahead. Whoops, not ready to do equations yet. Let's go ahead and do the free body diagrams, okay, for MA and then for MB. Okay, 2 objects, 2 free body diagrams. So for MA, that's the one on the table. So we have the normal force. And we have gravity, because it's a flat surface. So we have that normal force, and then gravity points straight down. We have tension. Okay, this was what we had before, with of course tension being the same for both, so I don't need a subscript. The one thing that changes is because it's going to be pulled to the right, we now have the force of friction, which I'm not going to add a subscript to because MB won't have friction because it's just hanging. So MB, it will look like this, Ft pointing up and then gravity pointing down. Okay. And so now we have our x and y equations. Okay. So in the x, we have F of t minus the force of friction equals ma times a. Okay. Then in the y, we've got this. For the second one, we've got nothing. And then for the y, we've got, oh, I'm sorry, I said down was positive. So plus minus for this guy. And then this one is Fg minus Ft. This will equal MBA. Okay? Now the signs are right. Okay. So we need to go ahead and solve for A. So solve for Ft in 1 and plug in solve for A. Okay, so ft, I would say, honestly, it's probably easiest to use this guy. So we're going to bring this equation down here. So we'll say f of t equals MAA minus the force of friction. And so now the second equation here is Fg minus Ft equals MBA. So now we can just take this guy and plop it in. Let me just make sure. Yeah, I got that right. Okay. So, force of gravity. Oh, this was for B. I should make sure I knew that. Always subscript, just in case. So this is minus MAA, and then minus, so this will be a plus the force of friction equals MBA. Okay, great. So now we need to solve for A, so I'm going to add that guy over. And if you remember, this problem is starting to resemble what we did before, right? Pull those out. This I can turn into MBG, right? Because remember, mass times gravity is the force of gravity, right? But now we have this force of friction here, which is just mu k times the normal force, which in this case was FNA. Because we're talking about the force of friction with the A box. Then this guy was MA plus MB equals A. So now what we can do, this guy, FNA, is equal to FGA. Okay, so you would write via the y equation above, right? So all you have to do is add this over. This would get added over, and you would see that they would be equal. Okay. And so we could just plug that in. And then this is going to be MAG. Okay. So now we can just divide that over. So A equal MBG minus mu K MAG over MA plus MB. We can do one more thing and pull out the G. So A equals MB minus mu K MA times G over MA plus MB. And as I was saying before, this is the exact same solution that we got for the Atwood's table, the regular Atwood's table, without friction, right? Same thing that we got before, only we didn't have this component. This is the friction component, so the frictional force, and notice it's minus that. So we're going to get the same acceleration that we got before minus the frictional component, which is how it should be for any problem that adds friction, okay? And so all the same things would happen before. If you reduce friction to 0, this guy goes down to 0, this whole component goes away, and you're left with the original system. Okay? So everything else stands. So cool. We know we probably did it right if it looks like this. So now all we need to do is plug in. MB, I believe, was 10 kilograms minus 0.25 kilograms. I'm just going to scroll up to make sure I did that particular one right. Yeah, 5 and 10. Cool. And so what do we get when we do all this? We get A equals 5.88 kilograms. Meters per second squared. Okay, because the kilograms cancel, and so we're left with just meters per second squared. Awesome. Okay, so that's how you do the Atwood's table with friction. And so now we're going to do our last example, and the last example I'm going to show you for forces. Call it example 3. And this is going to be a revisit of the inclined plane problem. So we're going to have a 70 kilogram skier that's descending a snowy ramp, and the slope is going to be 30 degrees. Okay. So we're going to have this be the setup, where this is 30 degrees. We've got our little skier. Let's make that a little bit better. Okay. We got a little, Santa hat. Okay, and so they're skiing down this slope. They have an acceleration this time. Okay, so we're actually given acceleration. We need to know what is mu k. Okay, we want what is the coefficient of kinetic friction between the ramp and the skier. Okay, and so let's go ahead and do our free body diagram this time. Okay, so free body diagram, we've got at an angle, normal force, gravity pointing down. Okay, and this was what we had previously. We're going down the ramp, so we'll have friction going up the ramp parallel to it. Force of friction, we can call it kinetic if we want to. And that's basically that. Okay, so now we need to add our x equations and our y equation. Okay, or x equation and y equation. So our x, I'm going to make down the ramp positive. Okay, we're going to tilt it just like we did before with a tilted coordinate system. And so in the x direction, we have the force of gravity, which is what's propelling us downward. And that's going to be force of gravity sine theta. Okay, because remember, the opposite, here's our angle, the opposite side right there is the x. Okay, so that's the adjacent side. So we'll want to use sine for that. If you're still struggling with that, watch the inclined plane video over that. We want to do minus the force of friction because that's pointing opposite. And this will be equal to mass of the skier times acceleration. Okay. And then for the y, we have Fn pointing up minus the force of friction, or minus the force of gravity pointing down, and this is the adjacent side. Okay, not the opposite side, so this is our y. Okay. And they're not accelerating through the incline, so 0, okay, for its acceleration. So these are our equations, and we want to solve for this. In this, we want to solve for the coefficient of kinetic friction. So we want Fg sine theta minus, if we unbundle it, we want to solve for this. So we want what is mu k, okay? So I'm going to add this over to the other side. And then I'm going to subtract over that guy. We can go ahead and call this mg again. So remember, Fg equals mg minus ma. So mg sine theta minus ma equals mu k Fn. So mu k equals mg sine theta minus ma over Fn. Now, what was Fn? Well, we have this other equation up here, Fn minus Fg cosine theta equals 0. So Fn equals Fg cosine theta equals mg cosine theta. So we can plug that in there. So mu k ultimately equals mg sine theta minus ma over mg cosine theta. Okay. We can cancel mass. Mu k equals g sine theta minus a over g cosine theta. So, what we've got here is our units are all going to be in meters per second squared on top, meters per second squared on bottom, right? And so our units will cancel, which is fine because friction is a unitless thing, okay? It's also not a function of mass because we don't have air resistance, okay? We could make this slightly easier, you know, maybe we could do sine over cosine, call that tangent, get rid of g. If you want to maybe reduce this a little bit, but I think it's fine as is. So this is going to be 9.8 meters per second squared times sine 30 degrees minus 4 meters per second squared over 9.8, and then cosine of 30 degrees. This will be mu k, 9.8. It's going to be 1/2. Just make sure this was 30 degrees. Yeah, 30 degrees. Cosine of 30 is root 3 over 2. So we get mu k, 4.9 minus 4 will be 0.9 over, this guy's 4.9 times root 3. Unfortunately, I've reached my limit of what I can do in my head, but this ends up being 0.1. So again, it's unitless because the meters per second squared will cancel. Okay, so that's it. We've got our coefficient of friction there. So that's pretty much it for the examples I have to show you about forces, including everything that we've covered up until this point. Remember that if you don't know how to solve a problem, do the free body diagram first, then do equations, and that should guide you, okay? I know we didn't do anything with static friction, but static friction is basically the same thing, only it hasn't moved yet. So static friction looks like that. Okay, this is just another coefficient. It's also between 0 and 1. You'll typically have these be higher, which explains why it's harder to get something moving than it is to keep it moving. That's why the coefficient of static friction is typically higher. But yeah, that's pretty much it. If you need more practice on forces, you know, there's the review and some other stuff to look at. Okay? So thank you all for watching, and I'll see you in the next unit, which is energy.